Hello everyone. Welcome back to the third part of the second module where we are talking about connectors, splicers and joints in the optical fiber waveguide. Okay, so why do we need fiber joints? So it is not possible to have an ever-ending optical fiber waveguide. So it is possible only for up to 200 kilometers. So during 200 kilometer span, there is a possibility that it is going to suffer breakage or any other loose contact. So it is very evident that we have to use joints at certain intervals. Optical fiber links with the line communication system have a requirement for joining and terminating. So you have to make sure that you are able to join two fibers with the help of any other material. So let us see what and how we are going to achieve that. So we already talked about why do we need joints. So any breakage, as I told you in the class, there is a high chance that under the seabed, due to so many other reasons, the fiber might break. So the transmission and reception should not have any hampering in there. So fiber can only be installed in length up to 2 kilometers. Even though we have the range of 200 kilometers around the globe. So for 2 kilometers you have to have a joints which is needed. So maybe for repeaters or amplifiers we can use that particular joints. So in one go it cannot be installed, and all the fiber in the building cannot be installed as one continuous cable. So in order to avoid that, in order to accomplish an intermittent joining, we need joints there. So joints are needed to complete the network cabling, temporary access, and tapping is also a prime importance there. So what are the losses in the optical fiber through connections, which is defined the same as the previous equation, 10 log 10 pi by p naught, input power by output power. So different types of joints losses. So during the joining, we have, as I told you, intrinsic and extrinsic coupling losses, and intrinsic losses are caused by the inherent fiber characteristics, which I have seen in the last video, and extrinsic coupling losses are caused by joining techniques, source of loss fiber to fiber joints. So we are going to talk about extrinsic fibers joints. So first one is the Fresnel loss. I'll come back to that. Second one is the core misalignment. During the alignment, if there is any problem during the alignment, we have end separation problem or lateral or angular misalignments. So this is what it comes under. Lastly, we have fiber parameter mismatch. So core section mismatch, numerical aperture, and concentricity mismatch are also a possibility. So we are going to show and understand with the help of figure. Alright. So first one is the Fresnel loss. So remember, Fresnel loss, we have to calculate the R first. R is nothing but, with the help of this formula, N1 minus N. N is the refractive index of air, and N1 is the refractive index of the core. So an easy calculation which tells us R can be calculated here, and substituting R here will give us Fresnel's reflection at single interference. So loss at Fresnel is equal to minus 10 log base 10 1 minus R. So this is also needed to understand Fresnel return loss. So whenever you are asking the wave to move through a waveguide, so there is a possibility that the signal might return back. So when optical fibers are connected, optical power may be reflected back into the source fiber. So this is also a loss. So light that are reflected back into the source fiber are lost, and it is not considered. So we have to calculate the loss with the help of Fresnel's reflection return loss. So how are we going to calculate it? With the help of this formula. We have minus 20 log 10 1 minus n1 minus n0 whole square divided by n1 plus n0. N0 is the refractive index of air. I can write n itself like the previous formula. N1 is the refractive index of the core. Okay, this is one small problem where they have given core refractive index as 1.5, two fiber length with smooth and perpendicular edge prepared and butted together. assuming the fiber axes are perfectly aligned, there is no loss in the missile elements is considered, and calculate the optical loss in decibel at the joints due to Fresnel's reflection. So we are going to calculate R as the previous case. As I told you, R will be 1 by 0.04, and finally Fresnel loss can be calculated by this. A similar calculation may be performed on the other interference iron fiber. However, from consideration, the loss can be told as it is 0.18 dB. Hence, the total loss at the fiber joint is approximately double that. So, you need to remember that Fresnel loss into 2 will be the total loss. Okay, how can we reduce the Fresnel loss? You can have a gel in between the two air gaps in between the two fibers. So the gel has to have an index, refractive index, which is going to be matching. A matching refractive index of the core fiber, and refractive index gel reduces the step change in it simply says that there is no sudden change in the refractive index, so that uh, the the gel acts as a cushion and there is no abrupt change in the loss. Okay, so misalignment losses are of three types. One is longitudinal, there might be a small space. There might be a lateral misalignment, there is a small the axis don't coincide with each other, and here the axis also doesn't coincide, but there is a small gap and it is an angular gap. So these are the three types of misalignments. Usually they will be asking this, and the figure is appropriate. Next, there is a possibility that the radius doesn't match, and the numerical aperture doesn't match. Numerical aperture, as I already told you, how much light it is going to accept it. And finally, you have the refractive index profile difference. So this is alpha 1 and alpha 2, two different refractive indices which is not matched. So you cannot have two fibers with the help of with this kind of situations. Okay, these are the losses. This is a core diameter loss here, and this is numerical aperture loss, and this is refractive index profile loss. So you might face numerical problems on this, so kindly go through this slide. Next comes the fiber splice. Splice in the sense, in simple terms, how are you going to cut, like how we going to cut the fiber with the help of a sharp object. So there is an edge perforation need to be done, and then it goes through joining. So splicing is the technique of cutting a fiber so that we can have a join there. The optical fiber end preparation is where you have a mandrel and a rounded arrangement, and this is bent in such a way that the knifed edge initiates the crack propagation so that it can break evenly. So this is the cleaving step, where a small cleavage is which is made to happen here because of the knife edge, and it is butted together so that it is cracked open, so that upon applying force it becomes two fibers, and this is the cleave which is formed here so that we can have joints same as the previous one. This needs to be avoided. The lip needs to be avoided because it needs to have only smooth end face, or even this is a negative lip or the hackled surface. Okay, you have two types of splicing. Splicing, as I already told you, it is breaking. Fusion splicing and mechanical splicing. So in mechanical splicing, we have two splicing, V groove and spring groove splicing. Let us see what splicing types are. So we need to remove the plastic buffer coating. As I already told you, the optical fibers will not only have coherent cladding but also have a plastic sheath. We need to open that. Clear fiber end to end. We are going to clean it with isopropyl alcohol or rubbing alcohol, which removes all the dirt and the grease from the outer area. So after the fiber end is prepared, good fiber end preparation is vital if low splices is to be achieved. Low splice loss needs to be achieved. So these are the very two important parts. After that, we are going to use electric arc or tungsten filament in order to cut the fiber. So let us see how it is actually happening. So this is the fixed block, this is a moving block. Here the fiber is kept. These are the electrodes which is going to cut the fiber, and the moving block goes away from the fixed block, so that there is a cleave which is formed here, and the electrodes will carry current such that the filament will break the fiber into two parts without the lip or the hackled surface. So this is the lever and the micro positioner which tells the fiber needs to be moved with the help of the movable block. So this is one of the very important questions, and it is advisable to remember the figure as it is whenever they are asking electrical arc fusion splicing apparatus. This is the initial setting. This is the electrode after the electric arc, and then once this is cut properly, you are going to join it with the help of the same arc, and finally it is butted together to form a single fiber. Here everything will be matched. So we can have a phenomena where this is the arrangement and it is not likely to be seen. This can be used with the surface tension so that it can be aligned properly. So this is fusion splicing. So whenever they ask you about fusion splicing, one thing, second, and the third thing you are supposed to draw with the help of a proper diagram and explanation. So this comes under fusion splicing. Let us talk about mechanical splicing now. Okay, so you have a capillary tube. This is the optical fiber. This is a capillary tube inside which you have a small gap which needs to be maintained. So this is the cross section, and this is optical fiber, and this is having a resin so that this will hold in place. And the second one is V groove. I'm going to tell you where I am mentioning this. This is the first one was the tube splicing. Second one is the V groove. V groove is also simple. You have a V groove here in the substrate, and I'm going to place the two fiber with the help of an epoxy resin. Epoxy resin is like a gel which is going to blend these two fibers together so that the light can pass easily without any loss. So this is joined together, and above which there is a fiber plate which I'm going to keep it above it so that the fibers are joined butted together. Similar case we have with the elastomers. This is a cross section and this is the assembly. Outside sheath is used to align it properly so that there is no misalignments. Finally, we have spring groove. This is the two cylindrical pins. This is where the fiber is kept. All those cases we are going to have the similar arrangement, only one or two small differences we have. And this is the spring which is going to hold this in place. So this is where we have three different splices. So remember that this is very important, and mechanical splicing, under mechanical splicing, V groove and capillary tube splicing is very important. Okay, next comes couplers. How are we going to couple two fibers together? So there is a very good possibility that it is aligned interaction from core to core or surface to surface. Okay, this is where you split the fiber. One fiber is having two emerging outward directions of two fibers, that is 1 to 2, this is 2 to 1, and this is a coupler which is a star coupler. And star coupler extended, we have M to N, and these two wavelengths are added together in wavelength multiplexer, and it is demultiplexer. So these are all the possibilities when we are using fiber couplers. Okay, let us talk about very important 3 and 4 port couplers. So when, as I told you, we are going to join or we are going to break open the fiber for this purpose also. It is like plumbing which you use at your house. So from here to here, if the water is moving, I need extension which needs to be done here. I am going to use it as an opener here. So this is a possible fabrication technique for 3-port fiber coupler. Okay, 4-port is very important compared to 3-port. 3-port is what this idea is. 4-port is you have one port where the fiber is allowing the light to be wave guided, and it is supposed to go from 3 and 4. Sometimes there is a possibility that it comes back to 2. So we are going to see the losses at all the cases. So different losses have got different names. So this is the excess loss, which is 4 port coupler. We have P1, P3 and P4. Input power is 1, output power is 3 and 4. This is the regular loss. Okay, excess loss. Insertion loss is from port 1 to 4. Port 1 to 4. So you are going to consider only 1 and 4. First one was excess loss, insertion loss. Crosstalk loss is 2 to 1. This is where the fiber loss, the waveguide is allowing it to travel back. So 2 to 1. And finally, split ratio can be calculated by P3 divided by P3 plus P4. All this formula you need to remember. Very simple formula. So they will ask you a similar question like this. As 60 microwatt optical power launched, so input power is 60. 2, 3, 4 powers. This is P2, P3, P4. And determine excess loss, insertion loss, very simple, crosstalk and split ratio. So, I'm sorry. So substitute it here. Excess loss we have P1, P3, P4, and insertion loss P1 and P3. Insertion loss from 1 to 4 is P1 and P4, and split ratio and crosstalk are absolutely similar as the previous explained cases. So you are going to simply substitute P1, P2, P3, P4 and going to get all the losses in dB except the split ratio where you have P3 minus P3 divided by P3 plus P4 into 100. It will give you split ratio. Finally, you have star couplers where you have M to N or N to M. So this is a mix rod and this is a mirror in case you need to bounce back the signal back. Okay. Splitting ratio for star coupler is given by 10 log N, where it should be noted that the refractive star coupler N is equal to the total number of ports. N is the number of ports, right? This is an extension of 8 cross 8 star coupler. Okay. Last topic is the optical isolator and the circulator. We talked about splicing, we talked about joints, we talked about couplers. Now we are going to talk about isolators and circulators. An isolator is essentially a passive device that allows the flow of optical signal in only one direction. It doesn't allow the signal to come back into the, it doesn't allow the waveguide to receive the signal back again whichever it is sending. So prevents optical reflection in backward direction. So it is ideally refraining from crosstalk. So ideally an optical isolator should transmit all the signal power in the desired forward direction alone. It should not allow in the backward direction. So material imperfection in the isolator medium, however, do generate backward reflection, which is unwanted in the help of in the case of waveguide. Alright, so this is the example of optical isolators. We have this is three port isolator where we have one which is having which is allowing it to go through only one direction, that is either 2 or 3. Okay, so here in this case only from 1 to 2, 2 to 3 and 3 to 4. So this is the case, this is a reflected optical signal, and in case I want from 3 to 1, I have to use 3 and 1 isolator. So this is the 4 port isolator and this is the 4 port circulator. So this comes to an end of isolator and circulators. So I hope this helps. Thank you.